This is example 4.10 for the simply supported flash beam. This is the figure of a layout plan, the beam layout plan. This is the simply supported beam. So this here is also a simply supported beam. So from this plan, you can define this as simply supported beam. This is also as simply supported beam. And this beam is the secondary beam, and this is the main beam to this beam. Okay, this is beam number 2. This is beam number 1. So this is how you read the plan. Okay, so this is the secondary beam to this beam. Okay, to this beam. Okay, meanwhile, this beam, if you design this beam is the secondary beam to this beam. Okay, so when we bring this out, okay, let's say this beam, okay, so this is the beam. Loading from this beam acting on this B13 beam, okay, 13 beam acting as a point load, okay, point load here. Okay, all right, so here also is the simply supported beam. Okay, this is also simply supported beam. Same goes with this one. Okay, this is simply supported beam. Okay, so the reaction for this beam, okay, if you calculate the reciprocal reaction at RA and also RB, this RB goes to this beam. Okay, this beam is acting as a point load. So that is the simply supported beam. However, in this example 4.10, 4.10, this example, okay, you need to design beam 2BC. So this is 2BC. Okay, so this beam is under the brick wall with height of 3 meter, and the size of this beam is, the proposed size is 250 width, and the depth, the overall depth is 500, and the specification as given here. The characteristic strength 25 megapascal. The characteristic strength of the steel bar is 500 megapascal. The concrete cover is 30 millimeter. If not given, you need to identify or determine the C from the Eurocode based on the nominal cover from fire resistant table 4.1. Okay. Fire resistant 1992 part 1-2. Okay, so you need to determine, you can determine this nominal cover from the Eurocode 1992 part 1-2. Okay, if not given, but in this example the nominal cover is 30, the slab thickness is 100. It is suggested, okay, later in your design, the minimum slab is, the proposed minimum slab is 125. Okay, 125. Please design your slab thickness 125 millimeter and above, but this is for example purpose. Okay, so we use 100 millimeter. The finishes and services is 1.5 kilonewton meter square per meter square. The brick wall thickness is 112.5 millimeter. So this brick wall 3 meter height. Okay, the loading is 2.5, 2.6. The variable action from the Eurocode 3.0. The concrete density is 25 for the concrete with the reinforcement. The density is 25 kilonewton per cubic meter, and we assume the tension diameter bar, the reinforcement at tension area is 25. the compression bar is 12 millimeter. This is at compression area, and the shear length is 6 millimeter. So at first stage we propose this one is 25. Here is 12, and the shear length here is the 6 millimeter. The first step is to calculate the effective width. Okay, based on this clause 5.3.2.1 from Eurocode 1992 part 11 in page 58. Okay, this is the T-beam, and the width of the T-beam is 250 because the earlier proposed size is 250 here. Okay, 250. So this is the beam. You look from this side. Okay, when you look from this view, from this point of view, okay, this view you can see the T-beam from here. Okay, this is the T-beam. Okay, the T-beam. So this is 250. The B1 here, our B1 here, so this is B effective. Okay, so first step we need to calculate the B effective. The B1 here, so this is B1. Okay, so from here to here, the B1, okay, is B1 is equal to 3500 divided by 2. So this is your B1. Okay, so meanwhile for B2, okay, B2 here, B2 is equal to 2500 divided by 2. Okay, so B1 is 1625 and B2 is 1125. And the LO is 6000. So this is the LO. So we read our LO from this side. So when determine the LO, you must view from this side. Okay, so this is your LO. Okay, LO here is 6000 here. Okay, thus our 0.2 LO is equal to 1.2 meter, and the B is equal to, this is our B. Okay, B is from here, actual width, yeah? So this is the B. So B is the total of B1 plus B2 plus the 250, yeah, the width web. Okay, the web width, yeah. So equal to 3000 millimeter. And thus our BEFF, the BEFF is the total of the B effective at 1. So this is the B effective 1. So here is the B effective 2. Okay, B effective 1 and B effective 2. Okay, our first B effective, you refer to the Eurocode page 58 kan later. So the equation is 0.2. Okay, multiply with the B number 1 plus 0.1 divided by and multiply with LO. So our 0.2 here, the B here, the B1 here is the 1625. So the B1 and 0.1 multiply with this LO. Our LO here is 6000, and you need to check this answer. So this outcome need to be compared with the 0.2 LO. Okay, so we go down. Okay, so the answer is 925 millimeter. Okay, 925 millimeter. So this B1 is 1625. B2 here is 1125. Okay, 1125. And our B here is 250. Okay, and total B, this is our total B. Our total B here is 3000. Okay, here is 3000. Okay, kita dah calculate atas lah. Okay, so next step is to find this B effective. First, we determine this B effective at number 1 and then B effective number 2. B effective number 1 is using the equation and we get 925 millimeter, which is less than 0.2 LO, which is 1.2 meter. Okay, and B effective at 2 here. Okay, we get 825 millimeter, which is less than 1.2 meter. So this one is L multiplied with 0.2. Okay, and the B effective, finally our B effective is 925 plus 825 plus 250. Okay, so this is our B effective, from here to here. Okay, so you totalkan semua ini you semua totalkan. Okay, and we get 2000 millimeter, and compare with B, must compare with B, which is less than B, thus 2000 meter is okay. And finally, this is our cross section. 3000, here is 250, okay, 250. Okay, this is our dimension, okay, for the T-beam. And the depth, the overall depth of this beam is 500. Okay, sebab kita earlier propose 250, 500, yeah. Okay, done. So this is the first step. Okay, next is the action on slab. Okay, you need to analyze, do the load distribution for slab to beam. Okay, so this beam, okay, this beam we receive load from slab plus self-weight of beam plus the wall. Okay, so this beam we receive loading from slab, self-weight of beam, its own self-weight, and also the wall. So this first you need to calculate the slab. Okay, this is the slab, self-weight of the slab, the concrete density multiplied with the 0.1, okay, equal to 2.5 kilonewton per meter square. Okay. Okay, then finishes and services depends on the use of the floor, and then you refer to the Eurocode. The finishes and services is 1.5. The characteristic permanent load, finally you get about 4 kilonewton per meter square, and the characteristic variable load is the 3 kilonewton per meter square. Okay, so this is GK, okay, from slab. This is QK from slab. So this 4 is the total of this 2.5 plus 1.5. So we distribute this loading, the slab loading, from this floor and also this floor to this beam based on the Ly divided by Lx. And it is determined that for this slab it is one-way slab and this slab is two-way slab. So I shortened the discussion because you know how to determine the one-way slab and also two-way slab. And according to the table 3.15, okay, so you distribute this loading based on this ratio, okay, this ratio, okay. So and finally we get the distribution action from slab to beam characteristic. So this is the GK is 23.28 and the QK is 9.74, okay, 9.74. Thus the total design action on beam okay, is equal to 1.35 GK plus 1.5 QK, 46 kilonewton meter. Okay, so This GK is a combination of the beam self-weight, the brick wall, and also the loading from slab number 1 and slab number 2. And this is the variable action QK is from slab number 1 and slab number 2. So this is slab 1 and this is slab 2, loading from slab 1 and slab 2. Okay. Next is the analysis. From this loading, we analyze for this simply supported beam. The VED is, for the maximum shear, is the FL over 2 and unit in kilonewton. Meanwhile, for the moment maximum, which is design moment, okay, so the formula is FL power of 2 divided by H, okay, WL over H, WL power of 2 divided by H. Okay, so this is the maximum value for the shear. Later you will carry this value to the shear checking, and also this 207 is the maximum moment, and this is MED, and this MED is used in the flexural checking capacity, and also to determine the AS, and also AS prime is required if required, AS prime too. So next is to design the main reinforcement. So D is equal to 451.5. So this is the T beam. Okay, and our overall depth is 500. The proposed diameter for this steel reinforcement is 25, and our shear link here, the proposed shear link here, the diameter is 6 mm, okay, and the nominal nominal cover is 30. Okay. Alright, so the D is from the top surface, okay, to the center of the reinforcement. So this is the D, okay. D, so this is the D. So 500, this 500 minus concrete cover, which is 30, minus the diameter of the shear reinforcement, and minus this main reinforcement, which is 25 divided by 2, and this is your D, and the calculated moment design is 207, okay, this value. And the moment at flange is equal to 1138 kilonewton meter. Okay, then we get that the moment at flange is more than moment MED. Okay, moment MED. So this neutral axis there lies in flange. Okay, so this is the neutral axis for this case. So when it lies in flange, so the conclusion is you need to design it as rectangular beam. Okay, so we proceed with the design. Okay, the checking and also the AS required. Okay, so this one is the K. So we get the K is equal to 0.02. Okay, 0.02. FCK is given, B is known, G also is known. Okay, just substitute all this value into this equation, and you get 0.02. Okay, 0.02, and the Z is this equation, and we get about 0.98D, and you need to compare this value. This value should be less than 0.95D. Okay, so the checking is similar with the rectangular beam. So please check, does this level arm Z must less than 0.95D. For this case, this value is more than 0.95D. Thus, we bring forward this 0.95D to the next step. Okay, we bring this to the next step. If the level arm Z is less than 0.95D, then you use this value. Okay, so the checking is Z must be less. Oh, kenapa tak dilukis? Sekejap must be less. Kenapa ni? Sekejap lah, saya tak boleh conteng. Okay, Z must be less or equal to 0.95D. So this is the checking. Okay, so then we proceed with the area of tension reinforcement as required as the M divided by 0.87 FYKZ. So this is the known value. You substitute this Z with the 0.595D and we get the AS required is 1110 square. And we check the minimum and maximum reinforcement. So we get the minimum reinforcement is 151 and also the maximum reinforcement is 5000. Thus our AS required, okay, is larger than AS minimum, but and also less than AS maximum. So okay lah. Okay. So then we provide based on this 1110 square. Refer to the table, the steel area table, and we provide our steel reinforcement at tension area 1473 millimeter square, where the number of this steel reinforcement is 3H25. Okay, 3H25. This H is for the steel reinforcement characteristics with the characteristic strength of 500. If you use 500 megapascal Newton per millimeter square, your label here is H. Okay, all right. So then this is the arrangement of the steel reinforcement. Next is the shear reinforcement design. Okay, the earlier analysis, the shear design, the maximum value is 138. Then next we determine the shear resistance. So the shear resistance is based on this equation, similar with the rectangular beam, and we check the code. Okay, the code for this one, based on the code 22 degree, the resistance shear is 318. And based on the 45 degree, the theta, the code is 1. So the shear resistance is 457. And then we check our VED kan. This is VED. The VED, is it less or more than VRD? So in this case, our VED, okay, VED is less, okay, than the VRD. Okay, so it is less than VRD. Okay, so it is okay. Kalau if VED is more than VRD, you need to redesign. Okay, in this case, in this example, we meet this requirement. Okay, the VED is less than VRD, but which code you want to use? Either 2.5 or 1. Which angle do you need to use? 22 degree or 45 degree? Okay. So between these two angle, okay, okay, for the next checking, we check the VED. Okay, if the VED compare with this code here, okay, so VED, when we check this one with the VRD, due to the theta 22 degree, okay, and also this is the VRD due to the theta 45 degree. Okay, we check this one. Okay, our VED is 100 138, okay, which is less than the code here. The code here is 318 and the code here is 457. Okay, the shear resistance due using the code 25 here, and here is code 1. Okay, our VED is 138, thus this VED is less than this one. Okay, if situation number 1, if this VED larger than 318, for example 400, okay, if larger than 318, so you need to use this one. Okay, however, in this case, our VED here is 138, which is less than 318. So we proceed with this angle. So thus our angle is 22 degree. Okay, so from this angle we proceed with the shear links. Okay, for shear links. So shear links, this is the equation for the shear link. Later you can refer to the rectangular beam. It's same procedure, same formula. Okay, so the VED 138, okay, divided by 0.78 FYK 25, D is 452, multiply with the code 2.48. Okay, 2.48. Nanti you gunalah trigonometry kan, guna calculator. You dapat kat sini lebih kurang 2.848 ataupun 2.8 sama je 2.5 If you use 2.5 here also, you akan dapat the same answer lah, 0.313 Okay, so then from this AS W over S we get 0.313, and we need to solve this equation by propose the area for the shear link. Okay, for the H6, okay, for the H with the diameter 6, H meaning here is the 500, the strength is the 500. The 6 here is the earlier proposed diameter for the shear link, and based on the shear reinforcement area, we propose the area for the shear reinforcement is 57. Okay, you can refer later in the table. Okay, 57, and when we substitute this into this equation 57, then finally we get the S is 182. Okay, 182. When compared with the 0.75D, the value is 339 millimeter. Okay, 339 millimeter. Okay, so it is okay. Thus, we provide H6 spacing from one shear link to another shear link. The spacing distance is 150. If you still remember, we need to provide the spacing increment of 25, 25. So the nearest lower 25 from 180 ni kan, kita buat is 150 kan. Okay, so 175, then we have here 200. Okay, 200. Okay, so the nearest also we have 175 here, but in this example it choose 150. Okay, boleh. So we select the smaller value. Okay, select the smaller value. Okay, next is the minimum links. Okay, why we need minimum links? Okay, you need to check minimum links. Okay, this is the minimum links, and we get the ASW over S for the minimum link is equal to 0.20. Okay, then we try propose the area, the same area with the shear link here. Okay, 57, and the spacing for the minimum links is 283, and we propose 275. Okay, 275. Okay, please make sure that this spacing is compared with the 0.75D. Okay, boleh ya. So thus, when the this spacing, okay, so for the minimum shear resistance of minimum links, okay? So this is a minimum links, okay? So we provide the minimum links from here to here. Okay, so how much the shear resistance at this point, okay, at this point. So this is the equation, and finally the result for the V shear minimum is 90. Okay, 90. Thus, okay, we provide the shear link from here up to this, okay, H6 150. So similar, same with this part, okay, H6 150. Meanwhile, this is the shear is decreasing, okay, and thus we provide the minimum link, okay, with the spacing 175. So dia lagi jarak lah, the spacing lagi jarak lah, okay, compared to this one dia agak dekat, okay, because shear at support is large compared to shear at the midspan. So for the economical to reduce the cost, so we did not provide the same spacing for the whole span, okay, when we consider the shear here, okay, it decreasing. So to reduce the cost, we provide the minimum spacing for the shear link. So next is the additional longitudinal reinforcement. Okay, additional longitudinal is based on the clause 6.2.3 number 7. So we first calculate this additional tensile force, which is 172.5. Okay, you calculate this one first. Okay, so this additional tensile force must be checked with the moment maximum divided by Z, M over Z, MED over Z. Okay, the MED over Z is 483, and we get this 172.5 here is less than 483. Okay, thus we provide this additional longitudinal reinforcement. Okay, so this additional we provide about the area is about 396 millimeter square, and to be added to the AS near support after curtailment after curtailment. Okay, selepas after steel cutting lah kita punya arrangement kat detailing tu. So next is the deflection. Deflection is checking based on the clause 7.4. So our checking for the deflection, our L over D actual, okay, must be less than L over D L over D allowable yang dibenarkan. Okay, so this actual, this due to the actual loading lah. Okay, so this is the equation. Okay, so first you need to calculate the percentage of required tension reinforcement, then calculate the reference reinforcement ratio, then calculate the percentage of required compression reinforcement. Okay, using this formula. So from this percentage of required tension reinforcement, later is compared with the reference reinforcement ratio. Okay, from this reference reinforcement ratio, we finally determine that this value is more than this value. Thus, we proceed the allowable L over D with equation 7.16b. So please refer this equation from Eurocode 1992 Part 11, clause 7.2.3. for 7.4.2. Okay, alright, then this K from table 7.4, and for the simply supported, the K is equal to 1, and substitute all this value into this equation. Okay, and finally we get the allowable, L over D allowable, meaning allowable also is the maximum or the optimum, is 14.8. However, you need also consider this with the 3 modification case. So the first one is the flange width. If this ratio, the B over the B web, is more than 3, so you need to modify this 14.8 with 0.8. Okay, so in this case, okay, our B is equal to 3000 divided by 250. Okay, so this is 3000 divided by 250, and the B is equal to 12. 12 is more than 3, thus you need to modify 14.8 with 3. Okay, so we modified 14.8, okay, darabkan dengan multiply with 0.8. Yeah, so this is L over D allowable. Okay, so next checking is the factor for the span. So our span is 6,000. Okay, the span is 6,000. So if it is 6,000, no need to modify the L over D due to the span. Okay, due to the span. If more than 7 meters, so you need to modify it with the span. Okay, with the span, which is L over 7. L over 7. So this L over 7 for the case if your beam span, okay, the span of the beam is more or equal to 7 meter. But in this case, in our case, the span is equal to 6 meter. If you look back to the layout plan, okay, this is the layout plan. So the span is 6 meter. Thus, no need to modify the L over D allowable, okay, based on the span. Okay, so yang ini equal to 1 lah. Kalau tak ada, if there is no modification due to the span, okay, so the here is 1 atau you tak payah tulis apa-apa, okay. So next is the modification factor for the steel array provided. So we check the AS required provided divided by AS required should be less than 1.5. If less than 1.5, you need to modify the L over D allowable with this equation. Okay, AS provided divided by AS required. So this AS provided and AS required is equal to 1.33, and finally we get this allowable L over D after modification is 15.7. Okay, 15.7. And then we compare with the actual. Okay, with the actual. Okay, we compare with the actual. The actual deflection, okay, is 13.3, which is less than the allowable L over D, which is 15.7. Thus, it is okay. So the deflection checking is okay, adequate, safe. Okay, apa sajalah yang note you kena letak. You should state this one. Okay, okay. Yeah. Next is the correct checking based on the clause 7.3, and from this table 7.1a, and the limiting correct width is 0.3 millimeter. And we know earlier that the GK is 23.3 and the QK is 9.7, and the steel stress, okay, the steel stress from the table 7.3N and also 7.2N. Okay, so you need to use 7.2N or 7.3N. In our case, we refer to the spacing only, which is from the table 7.3N. So in 7.3N, you need first to determine the steel stress. Okay, so this steel stress, okay, based on this equation, is equal to 285 Newton per millimeter square, and this lambda here is based on the moment redistribution. If there is no moment redistribution, thus this value is equal to 1. And solve this equation and we get the steel stress is 285, and we bring this value to this table, and finally we get the maximum allowable bar spacing is 100 mm. So this is the 100 mm. So here is 3H25, okay, and we have here is the shear link. Okay, this is the shear link. Our shear link here yang tadi tu berapa ya? 6. Okay, the diameter for the shear link is 6. Okay, H6. Okay, and the nominal cover here is 30 millimeter. Okay, and this is the spacing. Okay. Okay, the bar spacing. So this is the allowable, which is the maximum value for the bar spacing. Also is known as the optimum, okay, bar spacing. So we need to compare this with the actual spacing. So this is the actual spacing. The bar spacing is, so our B here is 250. Okay, 250. Okay, you minus this side and this side, which is the concrete cover, minus 2 multiply with 30, double concrete cover. So we have here 3 millimeter and also 30 millimeter, minus 2 shear link diameter here and here. Sebab kita nak pergi sini kan. So double 6, 12, minus 12. So minus 25. 25 is half of this steel area, half of this steel area. Okay, so this 25 divided by 2, 25 divided by 2, and this 25 divided by 2 plus 25 divided by 2 equal to 25. Okay, 25 and divided by 2 because we have two sides. Okay, this spacing and this spacing, so divided by 2, and this is the actual spacing based on the steel arrangement. Okay, steel arrangement. This actual spacing based on the arrangement, and this optimum spacing based on table 7.3N. So we check the actual spacing must less than the allowable spacing. So in this case, here is 76.5, less than 100. Thus it is okay, adequate, safe. Anything lah that can show the conclusion of this checking. Okay, boleh ya. Next is the detailing. So this is the detailing. Okay, so for the continuous beam, for the simply supported beam. Okay, here is the beam with the length of the span of the beam is 6,000, and we provide the main link, okay, 2H25 plus 1H25. Okay, kenapa ya? Why? Okay, so this is the beam kan. We know the maximum moment. Okay, this is the maximum moment. Okay, the maximum moment occurs here, so it at here. Okay, this is the maximum moment, but when it goes to the support side, it starts to decrease. Okay, it decreasing. from 0, increase here, maximum, then decrease back. So this here 0. Okay, so for the same purpose with the minimum shear link, so to reduce the cost, okay, we reduce the steel area at the low moment. Okay, at the low moment. Okay, so here even though, okay, we provide 3, okay, so if saya padam sekejap ni ya. Okay, this is our 3, okay, 3 bars, but from a certain distance, so we do the cutting from this distance to this distance, okay, about 480. So this is 480. Okay, later you can refer to the chapter 4 part 2, yeah, how we calculate this keteman kat here, cutting kat sini. Okay, so we provide here is 3, okay, 3 H25, and here is 2H25. Okay, 2H25. Okay, kalau kita pandang dari atas kan, if you look from the top, okay, the arrangement, if you look from the top, so this is the two reinforcement, and here is the 3. Okay, so jarak kat sini, the distance from here to here is about 480, yang inilah. Okay, because at this midspan the moment is larger compared at the support. Okay, the support is almost from the midspan, then at support is equal to 0. Okay, so that is the arrangement of the steel reinforcement. Okay, and then this is the 2H12. So earlier we decide we use only tension area, okay, tension area. Okay, even though in the design you only design as singly reinforcement, okay, so in order to place the shear reinforcement, you need something at the top to tie this reinforcement. Okay, to tie this reinforcement, to make sure that this shear reinforcement is placed correctly lah, accordingly lah. Okay, sesuai lah kat situ kan. Okay, so we provide the minimum compression reinforcement here. So earlier we proposed diameter 12, then just provide 2 because we need 2 di tooth area. Okay, so idea kita ni 1, 2, 3. So idea kita ikat dia macam ni. Okay, ataupun kita ikat dia terus macam ni. Okay, so okay, this is reinforcement lah. Okay, so you need this 2 top even though you design it as a singly reinforcement, to make sure that this shear shear link is well placed in the concrete. Okay, so this is the spacing for the shear link. Okay, so this is the shear link and this is the minimum shear link, and here is the shear link with the distance spacing 150, 275 and 150. So this is the cutting 480. Okay, 480. Nanti you lihat balik nota. Later you refer back to the chapter 4 part 2. There is the cutment lah. Okay, pemotongan sumber dan sebagainya lah. Okay, so that's all for that's all for this example 4.10. Thank you.